My name is Mauricio Rodríguez-Mayorga. I'm working under the supervision of Dr. Marc Torrent and Fabien Bruneval at CAA Paris-Saclay, and today I'm going to talk about improved density matrices from GW approximation. First of all, let me introduce what is a first-order reduced density matrix, the 1RDM. It can be defined as the product between the wave function as its complex conjugated, integrated over all coordinates except for x1 and x1 prime, and multiplied by n the number of electrons. The diagonal part of the 1RDM is nothing but the electronic density. The 1RDM is usually expressed using a basis in the following manner, where these coefficients can be computed as from the expectation value of the usual creation and annihilation operators. For closed-shell restricted calculations and non-interacting systems, like Conch and DFT, the 1RDM takes these very simple expressions where we just need to sum over occupied orbitals. Our goal in this work is to produce an improved density matrix built from two components, the density matrix obtained from Conch and DFT, plus some correction coming from GW. So what is GW? It's an approximation applied to calculate the self-energy in terms of the one-particle Green's function. Thanks, that's not much informative, right? So first let me introduce what is the Green function. The Green function is a function of the coordinates of the electrons, but also of the coordinates on time, t and t prime. And it can be built as the expectation value of field creation and annihilation operators times some step functions that depend on the time differences. We notice that if we take the Green's function definition and we define tau equal to t minus t prime, in the limit when tau tends to 0 from the left, we only retain this term, which if we multiply it by minus I, we recover the expression of the 1RDM. Therefore, the one-particle Green's function can be considered as a time-dependent generalization of the 1RDM. This means that given the one-particle Green's function, we can produce the 1RDM. For a non-interacting system, which is usually denoted as G0, if we take the wave function as that of the Conch and DFT as later determinant and we plug it into this equation, we obtain, after taking the expectation value and integrated over spin, this expression for the Green function of the non-interacting system, where we easily recognize the part that in the limit when tau tends to 0 from the left recovers the expression of the 1RDM. So, the Green function of an interacting system can be recovered using the non-interacting system Green's function G0 and the Dyson equation, which takes this form, where this sigma is known as the self-energy. In one-shot GW approximation, sigma is usually defined simply as the product between the non-interacting Green's function and some screened Coulomb interaction. In this work, we have used the linearized version of the Dyson equation, which means that instead of using here the interacting Green's function, we place the non-interacting one. Therefore, we know all the ingredients on the right to produce our approximated approximated Green's function. The question is how to build the screened Coulomb interaction. Well, we know from the Cassida equation that it's possible to get excitation energies and the associated eigenvectors. The screened Coulomb interaction matrix elements can be written easily by using the standard electron-electron repulsion integrals plus some function that depends on the excitation energies and on the associated eigenvectors. Finally, taking the Fourier transform of this quantity, we can produce it and go and get it back on time. So, in our one-shot scheme to produce an improved density matrix, we first perform a Conch and DFT calculation where we obtain Conch and DFT orbitals and orbital energies. Then with that, we can build a non-interacting Green's function, and solving the Cassida equation, we can produce the screened Coulomb interaction. with these two ingredients, we can produce the self-interaction energy. Finally, if we apply it into our approximation, we can obtain our approximated Green's function and our newly developed 1RDM, the GW updated 1RDM, which we will simply call it as the GW at a given density functional approximation. After doing all the math, we arrive to very simple expressions of the new elements of the updated 1RDM, which are simply functions of the excitation energies and on the associated eigenvectors, where here I have used I and j for occupied and a and b for virtual orbitals. It's easy to prove that the trace of the 1RDM, which means that the sum of the diagonal elements of this new 1RDM, recovers the number of electrons. So now let's move to our test. For our first test, we use small GW to test on molecules. We implemented this scheme and we analyzed the local error. If we define the local error as the integral of the density or a trial density minus our reference density, which in this case is taken at the coupled cluster 1, we use 13 molecules in this test, and PV0 functional was employed with different hybridization scheme. So in average, here we have the average value of this local error against different hybridization schemes. And as we can see, in blue we have the results obtained for the 1RDM obtained from Constant DFT, while on red we have the results obtained with our updated density metrics. Clearly, there is an improvement for any hybridization scheme. Moreover, if we apply our GW approximation on top of Hartree-Fock, the results obtained are comparable to those of MP2. The best value for the hybridization was found to be around 0.5 for this test. And now let's test the non-locality. In order to test the non-locality, we have defined something like related to the intracule, which in this case will be the intracule of modulus vector u as the integral of the 1RDM evaluated at r plus u, and integrated also spherically averaged, which if we notice that for u equals 0, we recover the integral of the density, so this is nothing but the number of electrons. If we take the difference between a trial intracule and a reference one given by coupled cluster, we notice that at u equals 0, we will have 0 difference because all density matrices recover the correct number of electrons. So here we have, for example, the results obtained for CH4. In the case of CH4, we have plotted this intracule difference against u, modulus u, and in dotted lines, we have plotted the results obtained from constant DFT calculations, PV0 again, with different hybridization schemes, and also on Hartree-Fock. And then with solid lines, we have plotted the results obtained with our GW approximated density metrics. As we can see, there is always an improvement with respect to constant DFT calculations. Moreover, for this particular test, it turns out that our results are much better than the MP2, the ones obtained with MP2. Again, a value of 0.5, 0.75 for the starting point in the hybrid functional was found to be the best. So we have implemented the printing of WFN files in MoleGW, and now we have access to these newly improved density matrices that can be used in any post-processing program. Now let's move to solids. In the case of solids, we have worked with Abinit code. We have implemented this update of the density metrics, and we also implemented the printing of DEN files, so we have access to a visual scheme of visualization of the new density metric, of the new density. But we could also pass these DEN files to any code like Critic2, for example, in order to compute Q-time charges. So here we have, for example, the charges computed for a series of systems using where the charge of the atom in parentheses is given here, And for this particular test, we notice that in the case of ionic species, they experience a larger change in the charge compared to covalent ones. Now, let's move to our last test. In our last test, we have computed total energies in order to get new lattice parameter. We know that the total energy is a functional of the kinetic of the 1 RDM through the kinetic energy, but also on the external potential. It's a functional of density through the electron coulombic nuclear repulsion. It's a functional of the 1 RDM on the exchange and on the nuclear repulsion. But thanks to the Galinsky-Migdal expression, we know that it's also functional of the Green's function. We can recover the correlation energy from the Green's function. So, in this case, we have in this work we have approximated the correlation energy with the Galinsky-Migdal by using the non-interacting Green's function in this expression, and we arrive to this very simple expression for the correlation energy. Here we have plotted the results obtained for silicon, again for the energy minus the energy of the minimum for different values of the against different values of the lattice parameter. As we can see, the results obtained for PBE, for example, overestimates the value of the lattice of the experimental value for the lattice parameter, which is around 10.26 1 Bohr, while HAC06 functional produces pretty accurate lattice parameter values. As we can see, when we use our GW updated density matrix, in all cases there is an improvement and is much more robust independent of the starting point, and we obtain results that are quite close to the experimental data. So, in order to conclude with my presentation, here we have introduced an improved linearized GW1RDM, which is built as from the constant DFT 1RDM plus some correction, linearized correction coming from GW. The new density matrix does not require the use of the zeta vector method to produce an improved density matrix, and it can be obtained as a one-shot correction on top of any constant DFT calculation. For molecules, the 1RDM is already available in ModGW package and including the WFN files, which can be used in any post-processing program. And we have seen that a value for the hybridization, for example, for PBE0 of 0.75 produces the best results when compared with coupled cluster first-order density matrix. For solids, we have access to atomic populations, as I have shown before, and therefore for two charges. Using the Galinsky-Migdal expression, we obtain new total energies, and we can use that to compute and predict lattice parameters. Finally, this new updated density matrix will be soon available in a future release of Avinit coming soon. So with that, I would like to thank my two supervisors, Dr. Fabien Bruneval and Dr. Marc Torrent, to the whole group of the Service de Recherche Métallurgie Physique du CEA, Paris-Saclay, to the CEA, to the University of Paris-Saclay, and to all of you for your kind attention.